Hello, in this video, we will talk about probability. This is the first video in this probability chapter. So whenever we start a new chapter, we talk about the terms or the terminology used with that topic. Probability. The first definition you see is the definition of a probability experiment. A probability experiment is an action or trial through which specific results, counts, measurements, or responses are obtained. The next definition is the definition of an outcome. An outcome is the result of a single trial in a probability experiment. A sample space is the set of all possible outcomes of probability experiment. S is used to denote the sample space. You will hear quite a lot this expression, equally likely outcomes. So what does that mean? That means that each outcome of an experiment occurs with equal probability. And another term that will be used quite a lot is event. An event is a subset of the sample space. Any combination of outcomes, uppercase letters like A and B represent event. So at this point, you are wondering, wow, that is quite a lot. And yes, you are right. It is a lot. It's the terminology we will be using in this chapter. In order to understand what each one of these mean, actually, besides reading the definition, let's give examples. I know that this material, everything actually in mathematics, it's better understood when we are given examples. So let's take a look at some examples to better understand the definitions. Rolling a sided die or flipping a coin. These are probability experiments because these have specific results. For example, the results from rolling a six-sided die will be numbers 1, 2, 3, up to 6. And this is what we will call the sample space. And we will denote that with S. We will be using the symbol for the set notations. And when we put all possible outcomes, this is called the sample space. Each individual outcome. And if I come back to these definitions, we can see that all of these are equally likely, all of these possible outcomes. And we can create events based on these outcomes. Any combination of outcomes. An example of event will be rolling an odd number when rolling a six-sided die. The second example right here is the example of flipping a coin. Hopefully you see that for flipping a coin, the possible outcomes are head and tail. These are precise results. So the sample space for this one will be formed of two possible outcomes, and we will just simply write down head and tail, and that's how the sample space looks like. Okay, I already answered this problem right here, and let's just give an example of events. Here is one. We already gave the other example when we roll an odd number. When rolling a die, rolling a number less than 3 on a six-sided die. In order to express this, I'll simply say, well, I can roll a 1 and a 2. I need a number less than 3. So the event this example refers to is formed of 1 and 2. There are 3 types of probabilities. Probability of an event E, which is denoted P of E, can be classical, empirical, and subjective. The classical probability is based on the idea of equally likely outcomes. So for a classical probability, each outcome is equally likely to occur. In order to find such a probability, you will simply divide the number of outcomes in event E by the total number of outcomes in the sample space S. And this is the classical or theoretical probability formula. The empirical probability is based on observations obtained from probability experiments. You can recognize this easily because this one usually comes with tables, information recorded in a table, information recorded from observing some experiments. This is called empirical or experimental probability. Probability of E equals the frequency of event E over the total frequency. And at this point, you probably recognize this formula, and we use this when we created frequency distribution. And this was actually the way we found the relative frequency. The last type of probability is subjective probability. Probability is based on intuition, educated guesses, and estimates. So this one doesn't really have a formula because it is, as it says, based on intuition or experience, or it's more like an educated guess, okay? Now, what is interesting is that if an event is repeated over and over again, then the empirical probability will approach the value of the classical probability. And this is called the law of large numbers for probabilities. And that's why when we solve problems related to probabilities, we will apply this formula. Okay. And right now, if you think about it, if I ask you a question, what is the probability of getting ahead when you flip a coin? Well, you will most likely say 1 out of 2. You already apply this formula. You're not going to flip a coin 10 times, see how many times you get ahead, or maybe 100 times, or maybe 1,000 times to see how many times you'll get ahead. Because the more you will do it and then count the number of times, you will actually realize that you are getting back here and you are actually getting closer to 50% of the times. Why? Because you have only 2 outcomes in the sample space and only one of those outcomes is ahead. Let's take a look at this example. We are talking about flip 2 coins. This is a probability experiment. So when you flip 2 coins, you're thinking, okay, how will the outcome of such an experiment will look like? A great way to visualize the outcome will be by using what we call a tree diagram. So what I will do, I will simply use this diagram to see the outcome of this very specific experiment. So I will start with coin 1, the first coin, and a starting point. And also, well, the 2 possible outcomes when I flip a coin, the first coin, I have only the head and tail. Now, each one of the coin will actually be the task, right? But for each one of the coin, I will go back and use the outcomes of the previous task, in this case, the previous coin, as a starting point. So right here from this head, I'll get again 2 options for coin 2 and 2 options starting with tail. So my sample space for this situation, as this will be the sample space, it will be called the sample space, we know that, will be formed by all of these possible outcomes. I'll go by branches, so I'll have head, and then I have head, tail, and then I can have a tail first on the first one, head on the second, and the tail and the tail. So right here, I have my sample space. Whenever you have to answer questions like this, try to visualize the sample space because that can only help, okay? So at this point, what is the probability of getting 2 heads? Well, I will simply try to figure out the fraction. How many of these outcomes are with 2 heads? So I'm looking at 2 heads. It seems that only 1 out of 1, 2, 3, 4 total outcomes. So I'll just simply say 1 out of 4. Next question. What is the probability of at least 1 tail? Yeah, keep in mind, at least 1 tail means 1 or more. So I'm looking for 1 tail. I have 1 tail right here. I have 1 tail right here. I have 2 tails right here, which means I have actually 3 options and 4 total outcomes in the sample space. Next question. What is the probability of no heads? So I'll be looking at no head. This one has heads. This one has this. This is the only one that has no heads. So I'll just say, well, only 1 is favorable to this outcome out of 4. And then the next one is, what is the probability of exactly 1 tail? I'm looking right here for exactly 1 tail. Well, this is not exactly one tail. This one has exactly one tail, and this one has exactly one tail. So I have 2 out of 4, which means 1 out of 2. Here is another example. The table displays the number of company employees by their highest level of education. If an employee is chosen at random, find the probability that their highest education level is a doctorate. And then all these other questions, we will start with a doctorate. Now, as you look at this problem, you should recognize that right here we have a table in which we have all this information recorded, which means at this point we are dealing with empirical probability, because not all of these outcomes are equally likely. Empirical or experimental probability. So in order to answer the question, what is the probability that if an employee is chosen at random, his highest level of education is a doctorate? So in order to answer this question, I will simply add all of these values. And if we add all of these values, summation is 91. So probability that someone will have this doctorate, will be at this doctorate level, let's just write down this in words, is 3 out of 91. For an associate degree, we are simply looking at an associate degree, which is 23. So probability of associate is 23 out of 91. I will not simplify this. I will just leave it like that. Okay, leave it as fractions for now. A high school diploma, it will be 4 out of 91. What about a bachelor or a master degree? Well, there is something new here. So let's just see what should we do. Well, because we have a bachelor right here and we have the master's degree right here, I hope it makes sense that we will add these two and then divide by the total number, which is 91. So the answer should be 25 over 91 plus 34 over 91, or 25 plus 34, which is 59 divided by 91. And the same thing goes for this last question. I will let you complete that one. Before going over more examples, let's just look at some other definitions. Unusual event. An event A is called unusual if probability of the event is less than or equal to 0.05, which is 5%. So if that happens, A will be considered an unusual event. The properties of probability. First, probability of any event will be a number between 0 and 1. If the probability is 0, that event is impossible. If the probability is 1, the event will be certain. Most of the time, you will find numbers between 0 and 1. So think of this as a large scale on the number line. This is where you have 0, and this is where you have 1. And the probability is a number in between the 0 and 1. The probability will be very small numbers, decimals. You can see that here, okay? And because of that, whenever we deal with the probabilities, we need to round to 2 or 3 or even more decimals. The probability of any event is equal to the sum of the probabilities of the individual outcomes in that event, okay? This is an important rule. And also the sum of the probability of all outcomes in S must be equal to 1. This is true whether or not S consists of equally likely outcomes. Another important rule is called the complement rule. And let's first talk about this, and then we will go over some examples. The complement of an event A consists of all outcomes that are not in A. The keyword right here, not in A. To visualize this using a Venn diagram, you have A as a set, and here is our A. All that's outside or not in A, and this is this area, will be referred to as the complement of A. And the notation can be A prime, or I've seen AC, different notations. This is what we refer to as the complement of A. This is a very useful definition. We'll see how we will apply it in problems, because this is what it follows. The probability that A does not occur is 1 minus probability that A occurs. In other words, probability of A plus probability of its complement should equal 1. Look at this. These are all possible outcomes. The sum of all outcomes will equal to 1 in the same sample space. So because we have this complement rule, we can easily find probability of one or the other if needed. Sometimes we can find a probability of A, and then if we need probability of the complement, we'll simply subtract what we found from 1. Or if it's easier to find the probability of the complement, then subtract that from 1 to find the probability of the event. Before getting into more rules, let's try to go over some examples. Here is one example with a deck of cards. If you are not familiar with a deck of cards, make sure you analyze this image, and you will need to know a little bit about how a deck of cards looks like. That's why we have the image right here. Just a few facts. In a deck of cards, we have 4 suits, as you can see, and these all go from 2 to ace. We have 13 cards on each suit. We have 2 colors, black and red. We have some cards that are called face cards. So the cards that are called face cards are actually 3 per suit: Jack, Queen, and King. These are the hearts, these are the diamonds, spades, and clubs. A total of 52 cards, 13 in each one of these suits. So let's go ahead and try to solve a problem using this visual. A card is selected at random from a standard deck. Find each probability. Randomly selecting a club or a 3. Let's see, what does this mean? Probability of a club or a 3. You know you have 52 cards total. Let's see how many of these outcomes are clubs or 3s. I'm looking at clubs. Right here we have clubs, right? Clubs, 13. And how many of these will be 3s? Right here I have these 3s. Right here I have all clubs. So how many total? Well, I have the 13. And because I already counted these 3 on the 13, because this is overlapping, I'll just simply add only these 3 more. So the answer will be 16 divided by 52, which is 4 out of 13. The next question is finding the probability of selecting a red suit or a king. Let's just take a look at red suit. We have 2 red suits right here, and we have 4 kings. If you count all the possible outcomes for this, you see that you actually have 26. Half of the cards are red. So 26 plus the 2 kings that are not red. So you will actually have 28 divided by 52. And that will simplify to 7 over 13. Now, the next question is find the probability of selecting a 9 or a face card. Let's look for those outcomes. 9. I have 9 right here. And a face card. As I was saying before, face cards are these cards: King, Jack, and Queen. We have all of these right here. We have 3 per suit. So in this case, it seems that we do not have overlapping outcomes. So the probability of a 9 or a face card is actually 15. No, actually 16. 12 plus 4, 12 right here, and 4 right here, over 52. So it will be 4 out of 13. This is just one problem. We're trying to solve problems based on simply the definition of probability. We will learn more rules as we move forward, and we can apply those rules, but you'll be able now to solve any problems without thinking of the rules. Another popular problem will require you to visualize the sample space for this experiment, rolling 2 dice. Identify the sample space and the number of possible outcomes, and then find the indicated probabilities. In order to do so, you can just imagine you have 1 die and you can assign colors to it. These are the possible outcomes of the first die. These are the possible outcomes of the second die. And all you'll have to do is just fill in. I will use green for that. So I will say this is 1, 1, and then 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and so on. Moving on to 2, I will fill in this. You can do it vertically, horizontally, but these are all possible outcomes of this situation. It takes some time to do it by hand, okay? But after you have this, you can figure out how many total pairs you have, and you will see that actually you have 36 total pairs. And I will scroll down and show this to you. You can find these images on the internet if you don't want to do it on your own, but here it is, okay? And now let's see how do we use this to answer some questions. So here is our first question. What is the total number of possible outcomes? We already saw that we have 36, right? 6 times 6, 36. What is the probability that the total dots show 7? So I'm looking at the sum of the numbers in a pair. So I see 7 right here and 3 and a 4, right? I see 7 right here and I see 7 right here. And it seems that there is some kind of symmetry in here because 7 will be actually this diagonal. So all of these will show 7. I don't see anywhere else the summation of the dots equals to 7. So I will say 1, 2, 3, 4, 5, 6 out of 36, which is 1 in 6, is the answer to my problem. The probability of the total dots showing 7 is 1 out of 6. Next, what is the probability that the total dots will show a number which is less than or equal to 6? So I'll be looking at numbers that are less than or equal to 6. Well, I see that in this part, I have smaller numbers, and I do realize all these numbers will be actually part of the numbers that show a total less than or equal to 6. On this other part of the diagonal, all the numbers add up to more than 6. So I'll just simply count how many. So we have 15 over 36, and that will be the answer, and so on. One more type of probability that we will go over in this video is related to conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. Let's take a look at some very specifics here. There is a word given, and most of the time when we talk about conditional probabilities, this word will be there. So that's the easiest way to recognize that probability. Or if you are talking about a sequence of events, some that has already occurred, be sure to think of conditional probability, okay? Let's see the notation for conditional probability. It's, again, very specific. Look at this one. Probability of B given A. Let's go over one problem, trying to understand how to solve problems related to conditional probabilities. 2 cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. Assume the king is not replaced. So make sure you read this again if you need to. And let's try to see how can we find the probability that the second card is a queen. And we have a condition right here, given that the first card is a king and we know that the king is not replaced. So if I want to solve this problem and I recognize this as a conditional probability, thinking about it, I'm trying to figure out probability that I will get a queen, given that this has already happened. The king was already taken from the deck of cards and the king was not replaced. So I'm thinking, okay, how many queens are there? Well, I have 4 queens on the deck of cards. Okay. Now, how many cards total do I have there? Well, because the king was not replaced, I have only 51 cards. And this is the effect the condition has on the formula. This is our formula, the probability formula. However, because there was a condition and they tell us that the king was not replaced, we have to consider it. So this is how it affects the sample size. Here is another example with conditional probabilities. We will see more of these examples in which we will see tables like this. But for now, let's just see how can we solve the problem without knowing too much of the formulas and rules that we will actually be learning in the next video. The table shows the results of a study in which researchers examine the child's IQ and the presence of a specific gene in the child. Find the probability that a child has a high IQ, given that the child has the gene. So we look at this table and we see that we have high Q right here. We have normal IQ right here on this row. We have gene present and gene not present. And then we have the partial total and the grand total right here. Okay, so in order to solve this problem and find the probability that the child has high IQ, given that the gene is present, we'll simply have to take a look at a fraction. On the top, we are looking for this information, which is the high IQ and the gene present, which is 33. And on the bottom, we are not looking at the grand total because we have a condition right here. We have to look at only this column, the gene present, which is 72. So whenever you use a table, you want to make sure you are not using the grand total if you are dealing with a conditional probability. We will learn more and more formulas, and you'll be able to solve these problems using formulas. But at this point, you should be able to solve a lot of probabilities problem just by thinking of the basic formula for probability. And with this, we conclude today's video.